Hello students, welcome to the lecture of structure of atom. In the last lecture, we had studied about the quantum mechanical model of atom and the limitations of Bohr's theory. And in the quantum mechanical model, we had discussed about the Schrodinger wave equation where we came across the terms Hamiltonian operator, which was denoted by H, the wave function psi and the energy terms. So, by solving the Schrodinger equation in 3 dimensions, we had concluded that there will be 3 coordinates corresponding to 3 numbers n, l and m, which are the 3 major quantum numbers. N was the principal quantum number, L was the azimuthal quantum number and m was the magnetic quantum number. We will not solve the proper derivation of Schrodinger equation here because it requires higher mathematics and higher knowledge of quantum physics, but we will just work on the results, that is the quantum numbers. So, today we will discuss about the important features of the quantum mechanical model and we will move to the quantum numbers. So, features of quantum mechanical model. So, the first feature is the energy of electrons in an atom is quantized. That is, energy can have only specific values. The second point was the existence of quantized electronic levels is a direct result of wave-like properties of electrons. And are allowed solutions of Schrodinger wave equation. Okay. So, the first point says the energy of electrons in an atom is quantized. That is, the energy levels will have a specific value and the energy of the electrons will not be continuous. And the second point was the existence of quantized electronic levels is a direct result of wave-like properties of electrons. We had discussed about the wave-like properties of electrons in de Broglie's hypothesis, where he said that like electromagnetic radiation, matter also has both wave-like and particle-like natures. And these quantized electronic levels are found out from the solutions of the Schrodinger wave equation. So, this was the Schrodinger wave equation where this was the Hamiltonian operator, this was the wave function and this was the energy term. So, Hamiltonian operator, and this is the wave function, and this is the energy term. The third point was exact position and exact velocity of an electron in an atom cannot be determined simultaneously. So, the exact path followed by an electron cannot be predicted. So, this was the result of Heisenberg's uncertainty principle, which said exact position and exact velocity of an electron cannot be determined. So, this gives rise to the fourth point, the atomic orbital is the result of wave function psi of an electron. So, the atomic orbitals are the result of wave function psi, and atomic orbitals are the basis of electronic structure of atom. We had seen that in the Bohr's theory, Niels Bohr didn't explain the detailed atomic structure. He didn't explain about the arrangement of electrons in a multi-electron system. But from the quantum mechanical model, by solving the Schrodinger wave equation, we get the three quantum numbers which gives the knowledge of an atomic orbital, and these orbitals are the basis of electronic arrangement in an atom. This we will study further with the quantum numbers. The fifth point was the probability of finding an electron at a point within an atom is proportional to square of the magnitude of psi at that point. Okay. So, psi square gives the probability of finding an electron at a point within an atom. So, since we cannot predict the exact path of an electron, we can only talk about the probability of the presence of an electron at a point, which is expressed as psi square, and this is known as probability density. Probability density. So, from psi square, what exactly we determine that the probability of existence of an electron in the atom. Okay. So, from the value of psi square at different points, we can understand that in which region around the nucleus the probability of finding an electron is maximum. So, when we had solved the Schrodinger wave equation in 3 dimensions, this was the equation d2 psi dx squared plus d2 psi upon dy squared plus d2 psi upon dz squared plus 8 pi squared m by 8 squared into E minus V equal to 0. This was the Schrodinger wave equation. Okay. So, we had said that the Hamiltonian operator is the operator for partial double differentiation. So, from this we get this equation, and from the solution of this equation we get 3 quantum numbers. So, we will now discuss about these 3 quantum numbers. So, the first one is principal quantum number, which is denoted by n, and this was proposed by Niels Bohr himself. If you remember, we had discussed about the Niels Bohr theory, and there we had derived certain expressions of radius of the nth orbit, velocity of electron in an nth orbit, orbital frequency, time period, and most importantly the energy of the nth orbit. This nth orbit is the principal quantum number n. This was proposed by Niels Bohr. So, what is the principal quantum number? It describes the size and energy of an orbit. So, the principal quantum number describes the size and energy of an orbit. N always has integral values, and n will have positive integral values. Okay, 1, 2, 3 and so on. So, positive integral values, and these orbitals were also denoted with K, L, M, etc. So, principal quantum numbers denotes the orbits or shells. Okay. So, when n is equal to 1, this is called the fast orbit or K shell. When n is equal to 2, we call it the second orbit or L shell. When n equal to 3, we call it the third orbit or M shell. When n equal to 4, this is the fourth orbit or N shell, and so on. So these are the orbits. Now these have some significance. We had discussed that if this is the nucleus and this is an orbit, and if we consider the circumference of the orbit as 2 pi r, okay. So this is the total path covered by the electron. Where r is the radius of the nth orbit. And we know from de Broglie's hypothesis that when electron moves, it generates a wave. So this is in this form. And so we know that wavelength, what is wavelength, we had discussed earlier. So now if we try to find out that how many wavelengths are there in this total path. So if we write 2 pi r is equal to n lambda, that in the total circumference there are n number of wavelengths, then this n gives the number of waves. So if n equal to 1, then number of waves is 1, that is 2 pi r is equal to lambda. If n equal to 2, then number of waves is 2. If n equal to 3, then number of waves is 3. So from the principal quantum number, we can know the number of waves. And the formulas that we had derived, for example, the angular momentum. Angular momentum mvr equal to nh by 2 pi, and radius of nth orbit Rn equal to 0.529 into n square by z angstrom, where z is the atomic number. Similarly, we had derived many formulas of velocity, orbital frequency, time period and energy equations, all of which had n. So from the principal quantum numbers, we can predict all these values by putting the value of n in these equations. So the principal quantum number n gives us the result of many important properties such as the angular momentum, radius, velocity and energy equations. So now we know about the principal quantum number or the orbits. Now we will go further with the next quantum numbers. Thank you.